Right, so in the last class we had been looking at indexed color and how instead of using something like an RGB system where you have all the possible colors, you might have a limited palette of colors. And so if you've got 256 of those, for example, then you will need 8 bits for each pixel instead of 24 bits. So that's grand when the number of colors in the image is less than the number of colors in your palette. We saw in some examples and in the lab when you push the number of colors in your palette too low for the number of colors in the image, then some pixels are forced to go one way or the other. So light shade of grey might have to go to white or slightly dark grey if there's a limited range of greys. And so that can give you this banding, which can be unsatisfactory. So again, this is a contrived example here. But so when you have a small number of colors in your image and then you reduce the number of colors using indexed color, that's fine. But if the palette is really, really small, then you get this problem here. So what's happened here is that there was an intermediate shade of orange between here and here, but it was forced to pick. So every shade of orange in this image has to be either this or this. So every pixel has to be either this or 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 this. And forcing that choice creates that banding there, which is unsatisfactory. If we look here, this image uses dithering, and dithering is what we're going to look at today. So this image also only uses pixels from that palette of 8 colors, but it's much more satisfactory. But there's still no more than 8 colors, 8 colors of pixel in this image. And when we zoom in, we see what's happening. So dithering simulates the appearance of colors that are not in the palette by carefully arranging colors that are in there. And then from a distance, at least, they have the appearance of the unavailable color. So this is a big deal when your palette is limited. I remember when I was younger, coloring, messing on the computer, and it only had 256 colors. And I remember there was this tutorial on dithering and a little program on dithering, but it showed you how you could make any color, and it was amazing. You could do all these cool things, colors that had never been seen on the computer before. It was amazing. No. So here, I don't know if you can see it on your screen. Here on the left we have the original color, and then here on the right is the simulation of this color using dithering. You can't quite see it, but if I zoom in and make the pixels bigger, you can see them there now. So it's like little grains of salt on a blue tablecloth or something. Okay? And so the idea is that you don't have all of the colors that you need. So you can fake the color that you want using the colors that you have. This slide is screwed up. I don't know how that happened. I don't know what that's about. So we want to get a color that has a red value of 255, a green value of 118, and a blue value of 205. But we don't have that in the palette. We do have in the palette some colors that are kind of in that neck of the woods. And so here's what we've done here. So this pale pink here has a red value of 255, a green value of 153, and a blue value of 205. And this dark pink has a red 255, a green 102, and a blue 103. So what we're interested in then is what this would look like from a distance. So from far enough away, when they're blended together, we'll see the average redness, the average greenness, and the average blueness. Now, the average redness of these pixels is 255 because they're all 255, so we don't have to worry about the maths too much there. Similarly, the blueness is 205, so again that's a no-brainer working that out. To work out the average greenness then, we have to include the green value of the dark pixels 3 times and the greenness of the light pink 1 time. There's a ratio of 3 to 1 there. So the ratio must be preserved for it to make sense. So if you struggle with like the concept of a weighted average, this is going to wreck your head. And so that gives us, looking at it there, it gives us an RGB value of a green value of 115. Now the target, what we're looking for was 118. But 115 is pretty good. So this is a reasonable approximation of the target color. Okay. Here it's somewhat similar, but it's easier because they're in a 50-50 ratio. So at least the weighted average here is simpler to calculate. So the dithered color is going to look like the weighted average of the RGB values from the color in the pattern. So here we have a light blue and a dark blue, and what we would expect then was some sort of in-between blue. So the red value is 187 and 151, and 51, and the average there is 119. The green value is 225 and 51, and that averages out to be 138. And the blue value is 227 and 153. When we average that out, we get 190, which is this color here, which is kind of what you'd expect. Some shade of blue between this blue and this blue. It's not, looking at them side by side, it's not immediately obvious that if these pixels were smaller, that this would blend into that color there. I take off my glasses and it's kind of easier to visualize. But if you don't have glasses, you don't have that feature. Okay, so it's plausible anyway, certainly, that that's what that would look like. In Photoshop then, there were a whole bunch of options. Now some of these have since been depreciated. But in Photoshop you had the option of choosing, there was a palette specific to Windows and a palette specific to Mac OS, and there was also a palette that was a subset of a common subset of those that we used for the web. Obviously dithering isn't as big a deal as it used to be. The scenarios in which you have to resort to a very small number of colors are quite limited now. In the past, you had no choice because the display itself could only do 256 colors at a given time, and so you had to put a lot of effort into coding images so they would fit into those 256 colors, and you had to choose the 256 colors very well. But now it's not such a big deal. Let's skip past these. Obviously then with Photoshop, you can say to Photoshop, and you've seen this in the lab, you choose the best 256 colors or the best 16, whatever it is, give it your best shot. No. Here is a tougher one mathematically that I want you to think about, okay? So here we have 2 different colors of pixel. In a 3-to-1 ratio. Now the color that appears once has an RGB value of 255, 150, and 180. The target color that we're trying to represent has a red value of 200, a green 100, and blue 100. So on average, this turns out to be 200, 100, 100. And what is the missing color there then? That's a trickier one to work out. Is that something you think you could do? Have I given you the answer? I haven't, so I'll have to do it. You could do it like with proper algebra, where you say the red value, let's call it R, like 3R plus 255 all divided by 4 equals 200. Yeah? Does that make sense? We're just looking at the red value. If the red value that we want to figure out is R, then 3R plus 255 all divided by 4 equals 200. Another way to look at it, which is probably more intuitive, is if it's in a ratio of 3 to 1, okay? They all have to add up to 800. The red value's there. For them to average out at 200, if there's 4 of them, the total has to be 800. Now, of that 800, I'm going to regret now not having brought my phone this hour of the morning. I don't do maths very well. Do I ever do it well? 800, of that 800, 255 has been accounted for with that one pixel there that's already there. So there's only 545 remaining for the other 3. Yeah? Which would be whatever. So it's another way to look at it. Obviously, working out the weighted average of the pixels you're presented with is easy enough. Doing the job that something like Photoshop has to do, where here's a color, how might you dither it? That's not as easy. It's a bit like integration. I think sometimes it's trickier. So we'll crank up Photoshop there now, and we'll do a few little experiments on dithering.